All right, so anybody have questions before we get started, before I go into slides and talk about authentication? Yes?
When should we send the response, like the header itself with the ID only when it's cookie first made, or is that like an every response?
Only when the cookie's first made. So you send the set cookie header on the response only when you want to set the cookie, and then that cookie will come back on every request after that. You would only use set cookie again if you want to change the value of that cookie. So for example, your visit counting cookie, you're going to have to use set cookie every time the user requests the root path. You're going to set cookie again to increment the value of that cookie. But for authentication, for your authentication token, you're only going to set that cookie one time. And then you'll read it in every request that you get. You're going to read that cookie and say, okay, this is what their auth token is. And then look it up in your database, figure out who the user is, et cetera. But that cookie you would only set one time only. Yeah, that would be set on every request for the root path. I actually got this question after lecture. This is just worth pointing out. That cookie you would only set when somebody requests your root path and you're sending your home page. You don't want to set that on every single request, or else somebody visits your page, gets your HTML, CSS, and JavaScript. You don't want to count that as 3 visits. So only in your code that's handling requests for your root path, for your root HTML, you're going to read that cookie, increment it, and then set cookie again. But yeah, so you do that on every request for your home path. You would read the cookie from the headers, parse the cookies header, read the value of it, and then send back a set cookie for that same cookie name with that value incremented by 1. So for that one and that one only, every time you're handling that cookie, you're setting it again with the set cookie header. Does that make sense? Does that answer your question? Okay. And set cookie will overwrite whatever, if it's like a key value store for the cookies. If you set a cookie with the same name as a cookie that's already set, it's going to overwrite the value. The browser can't have 2 cookies with the same name. Any other questions? Oh, I don't have my phone out. You guys don't really use the Discord anyway much, but I do still have this open in every lecture. Lecture 116 uses it a bunch, so I always see the 116 comments in this class throughout the whole lecture. They never get pushed off the screen. Hey, anything else? Okay, let's talk about some authentication. So what we eventually want to build are user accounts. This is the big goal of Homework 5. This is objective 2, but it kind of creeps into the subsequent objectives. So we want to, with the tokens that we'll talk about on Friday. So this is what we want to build, user accounts. And we're going to have custom content, especially in the later objectives, for their users. This is how you experience the internet. You're going to log in, and based on your account, you're going to get different information. Whether you can change your account settings, view different content. Maybe you can only view content from your contacts or from your friends list or your follows list or whatever. There's going to be different content sent to a person based on their user account. We're going to do that using authentication and cookies. So that's our goal. That's our goal with the really Homework 5. User accounts are going to work in 2 separate paths. I guess they turn into paths in our websites. We're used to these from the user end, but we want to look at the other side and how this works on the server side. On the user end, you have registration. You're going to create a user account, give them either an email or a username, some unique identifier of you, and a password. Usually you have to type in your password twice and make sure they match and everything. But you're going to have your username and password is what that boils down to. Authentication, you're going to go back to that site and say, here's my username and password. And if they match the username and password that you used at registration. You're authenticated. You can use that app. You have that personalized content for you at that point. And then you get your specific experience from that app, which will be unique from anybody else's experience. I mean, depending on the app, of course. You're going to see your posts. You're going to be able to edit your posts, things like that. Depends on what the app is. For your homework, we just serve up, slightly different content based on whether you're authenticated or not. It just says hello, welcome, whatever username you have. But for your project, you have to do quite a bit more. Your project, you have to have DMs, for example, the DM feature. That really relies on authentication. If you send a DM to somebody, you don't want that DM, you don't want your server sending that DM to all users, of course. You want only that specific user to whom that DM was sent to be able to view that DM. So we really have to pay attention to authentication for the project because there will be a lot of different content, very different experiences depending on who you're logged in as. So, yeah.
I was just a curious question on, so like when you're signing in and it gives you multiple options of different services, like let's say sign in with Google and Facebook.
Mm-hmm.
As from like a developer's point of view, like how does that work? Are we like requesting Google to hold on to the information of the username and password, and then we'd create a user with no password? Or?
Yep. Yeah, so whenever you see like the login with Google button, so each one of those buttons on the back end, you'll have to have different ways of handling it to talk to their specific APIs. And most of them work off of OAuth, so it's pretty standardized. But you would not store the user's password at that point. If for anyone who clicks login with Facebook, login with Google, login with GitHub, whatever, you would not store that user's password. The login with, let's use Google as the example, login with Google. Google's going to store the password, the username. They're going to have all that authentication stuff on their servers. And when they click that button, they're going to log in with Google if they're not already logged in or they don't already have their tokens. And then Google's going to issue an OAuth token to us. It's going to say, okay, this user is logged in, they're authenticated, here's their Gmail address. Like this is a legit authentication, they're logged in. Then we just say, okay, that's good. We're going to create an account with that email address and just not store any password associated with it. And then whenever they visit our site again, we're going to talk to Google and be like, hey, is this person still authenticated? They're going to be like, yeah, here's a token to verify that. And then we're going to treat that as a legitimate authentication. So we're just deferring to somebody else and saying, you handle authentication. Just generally a good idea, at least good to have as an option. Because if login with Google was your only option for authentication, you don't have to store passwords anymore. You don't have to worry about securely storing passwords, which is the main thing we want to talk about with authentication. How do we securely store passwords? If you only support login with Google or login with GitHub, you don't have to worry about that. So there are advantages to that, but if that's an option, anybody who chooses that option, they're relying on Google for securing their passwords instead of whatever site you have. Some people like, as a user especially, it's something to think about. Do you trust the site to store your password securely, or do you trust Google more to secure your password? Plus, you have one less password to remember is always nice. It's always common to associate, this is pretty universal these days, to associate a user account with an email address. Email that email address to verify it, and once it's verified, you either unlock all the features of the app or you don't get any features of the app until you verify your email. This is pretty common. This is done to limit bots. I had a website, I think I mentioned this already earlier in the semester, that was just bombarded with bots, but it was all fake email addresses, and I had email verification on. So my app would send them emails to verify. They couldn't verify because they were all fake, randomly generated emails. So none of them could verify their email addresses. So they couldn't make any posts on my site. They couldn't actually do anything, but they were trying. The bots were creating these random accounts and getting the accounts made. So if you have email verification, it really limits those bots. It actually has to be somebody with a legitimate email address. Having a bot create email addresses, well, now they have to get through whatever defense the email provider has. They're probably going to detect that as a bot and start shutting them down and things like that. So verify email address, very handy thing on the web. I'm sure you've seen this from the user end, but that's why this is done. It's to prevent those bots from creating a billion accounts with fake email addresses and then just spamming the crap out of everything. We don't like that. A lot of web developers have, in the past, made that mistake. It's rare to see now because in classes like this, we tell you to verify email addresses. There used to be bots just everywhere. You make that mistake once, you don't make it again. You're going to verify email addresses, then you're going to pass it on to the next generation. So we verify email addresses. I'm not going to do the example, but on this slide, I used to actually go to that server and then show you all the email addresses. We'll have to visualize it today. I'm not set up to go. I don't think I even have that. Do I even have that server anymore? I don't know. We're not going to see the actual data, but it's a database, and I show you it was multiple per minute of bots that were creating accounts, and it was up for years. So tens of thousands, hundreds of thousands of accounts that were created. The math doesn't add up to. Maybe it wasn't quite multiple per minute, but it was a lot. It was in the, I believe it was in the hundreds of thousands of accounts. So on the server, the implication is that we have to store this username and password. Username, okay, whatever. We're going to store usernames. Passwords, this is where the conversation gets trickier. We have to store these passwords securely in our database, because if we don't, what if somebody gains access to that database? Maybe they have a successful SQL injection attack and they can read this database that's full of usernames and passwords. SQL injection attacks do happen. People are going to, can potentially read that database. The sysadmins that host this website, they can read this database. Any developers that have access to the database will be able to read it. They'll be able to get every username and password. Presumably you trust those people, but how much? Do we believe that they're not going to be malicious? That maybe the sysadmin knows somebody who uses your app and they want to, maybe their girlfriend just broke up or boyfriend just broke up with them and they want to get some revenge or something. Do we trust them to that level that they're never going to have a lapse in judgment and use that information for nefarious purposes? I don't know. I'd rather not. So what we want to do is store these usernames and passwords in such a way that even the sysadmin, even the executives of the company, even the developers of the app themselves can't read those passwords. That's the level of security we want, and that's the level of security we're going to get. So not just SQL injection attacks, but legitimate users, legitimate employees or whatever, developers, anybody working on this app and has access to the server still can't read those passwords and spoof them. That's what we want. Yeah.
I would see SQL injections, but for MongoDB, is there an equivalent?
Not really. No. MongoDB is pretty nice. MongoDB was built with this idea of, SQL injections really suck. It was built with that in mind, and they just really don't have the same thing. That's why I never talked about that with MongoDB. It really doesn't exist. There are some libraries, some specific libraries that handle the connections to MongoDB that have had security issues in the past. So certain libraries have. MongoDB itself has not. It's not that I'm aware of, had any equivalent to SQL injection attacks. But you got to be careful with the library you're using. I would imagine all the ones out there right now are fine. But there are libraries that have had problems in the past. There was a specific PHP library for connecting to MongoDB and sending MongoDB statements and queries that did have a security vulnerability because it was taking strings and then parsing them, which is the root of SQL injection attacks. It was taking Mongo queries as strings and then interpreting them and then sending the queries, which is always bad. You should be sending it in object. Like if you're using JavaScript, a little JavaScript object with all your commands in there, And then when you put the user data in there that they're requesting, it's literal values. It's not part of that object. So there's no string parsing going on to interpret those commands. Like if you use MongoDB, there's literally a .find method to be able to retrieve information. It's not a method that takes a string like SQL. SQL is a method that takes a string and says execute this query. And then in that query, you'd have select star from or select whatever you want from some table. MongoDB, it's literally .find, and then it takes your parameters as an object. So we don't have that same issue. But if the library you're using does parse, it takes a string and then parses it, that's a red flag. That's something that's going to open a security hole. And that's why we use prepared statements in SQL, because just by nature, SQL takes strings and then interpret them as SQL statements and parse them. So with passwords, we don't want to store these passwords in plain text. Our answer is going to be hashing. We want to hash these things. So a hash function is a function that takes in a value and then spits out another value, typically with some properties to it. And often, one of the properties we like with hash functions is fixed length. We want a fixed length value. This is very nice for building hash tables, for example. You want a fixed length value for the buckets in your hash table. So you have a hash table with buckets that are represented with 8 bits, for example. You want 8-bit length values coming out of your hash function, so you can so you make sure that everything hashes into one of those buckets. So that's one of the reasons we like hash functions. It's nice to build hash tables and a lot of other properties. Hash functions themselves do not necessarily add any security. If you just have some hash function and you apply that hash function to your passwords and then store them, it's not necessarily secure. You have to be very careful. This is just a misconception that I hear. It's a little bit of a nuanced point, but it's a misconception I hear often enough that I want to make sure everybody's aware of that. Hash function does not imply security. There are cryptographic hash functions, which I will add to the confusion a little bit. I'll just refer to cryptographic hash functions as hash functions. So when I say hash function, I always mean cryptographic hash function in the context of this lecture. But you can have a hash function that is not a cryptographic hash function, which would be, for example, any hash function used in 250 to generate a hash table. Those are not made for cryptography. They're not made for security, but they are still considered hash functions. They will not give you any security, because that's not what they're designed for. They're designed for efficient hash tables and efficient hashing algorithms. They're not made for security purposes. So we need a cryptographic hash function. Cryptographic hash function is meant to be a one-way function. You can put something into the function, you get something out, but you can't go from whatever you got out of the function and go backwards and reverse engineer this back to the original input. So this is the SHA-256 hash of the string password. If your password is password, that string is your SHA-256 hash. SHA-256 is a cryptographic hash function. And given this value, given that this is such a weak password, you could, but given this value, you wouldn't be able to brute force your way back. That's bad wording there. You wouldn't be able to compute the original input that generated that hash. This is the property we want from cryptographic hash functions. These are one-way functions. You can't go backwards through this function. This is an online tool that I like to use just to generate SHA-256 hashes. Let me visit it quick. If I get this value, 5E8848, ends in D8, we'll try to remember a little bit of that. If we go back to our slides on the previous slide, 5E8848, ends in D8, it's the exact same hash I have in this slide. This is the SHA-256 hash of the string password. This one I happened to generate using a Java library, and the other one that you just saw me compute was computed using JavaScript and a web front end. The algorithm for these hash functions is completely separate from their implementations. The algorithm is always the same. No matter what library, what language, whatever you're using to generate these hashes, that implementation has to follow the same exact algorithm. So no matter what you're using to generate these hashes, they all have to use the same exact algorithm. So no matter what we're using, if we hash the string password, we're going to always get the same hash. You might see, depending on your library, this is hex. So depending on your library, the letters might be capitalized or lowercase, just based on preference. But those are hex values. Capitalization doesn't matter for those. So just a heads up on that if you ever come across that. So if we hash, we do get that property. You can't go backwards. So even those admins can't see your password. Can't go backwards on these hash functions. I'm not going to go into the details of SHA-256. It's a lot of bitwise operations. And the outputs here go run back into the inputs multiple times. There were several passes. If you're interested, I'll let you read that on your own. But it's a lot of bitwise operations and a bunch of random, not random, but fixed bits, fixed bit arrays that you're XORed with multiple times, and then everything's shuffled around. Just a lot of random-ish stuff going on. It's deterministic, but it seems random to us for a human. And it's built in such a way that nobody's publicly announced that they've figured out a way to reverse this process. Very careful with the wording, because it's very possible that some hacker out there has broken SHA-256 and just never told anyone, and they're just wreaking havoc all over the place. It's possible. I'd say it's unlikely, but it's possible. So there is a problem here, is that you can actually break hashes. You can't simply compute the input given a hash, but there's a very simple attack called the brute force attack. You can go very quickly forward through the hashing algorithm. The hashing algorithm is made to be fast. There are libraries with very nice implementations. There are libraries that run on GPUs and can do tons and tons of computations per second. So you can always go forward very fast. So what we're going to do is just guess every possible password that you might have come up with, hash every single one, and then once we find one that matches the hash, we got your password. We didn't break SHA-256. We didn't break any cryptographic hashing functions. But we just used the hash function for its intended purpose, generating hashes of plain text inputs, and we're able to figure out what your password is if you have an insecure password. So this is why, even though we're storing hashes of passwords, this is why you always have password criteria, uppercase, lowercase, number, special character, at least 8 long is the common criteria. That's why we have those criteria on every site still, because if you don't have a strong password, if your password is just the string password like we saw in the previous slide, super easy to guess. You're just going to go down there, you're going to get a list of the most common passwords, the most commonly used passwords, hash all of them until the hash matches. If you have an insecure password, if you have a weak password, even somebody with the hash of that password is going to be able to figure out what it is. Not by breaking SHA-256, but just by brute force attacking your hash. This is a surprisingly common misconception. This is much more dangerous than maybe equally as dangerous, but more, I don't know, it's scarier to me, than the misconception of hash function means cryptographic hash function. This one I've seen in peer-reviewed, accepted papers where the authors were like, don't worry, man, we hashed it. It's fine. Nobody can read that. We hashed it. And then the values had like almost no entropy, which is a term I haven't quite introduced yet. But effectively, the things that they were hashing were very, very weak passwords in essence. And the paper literally said, like, don't worry, we hashed it. Nobody can read these things. I'm like, brute force attack would crack that in less than a second. Like, how do you say that this is secure? And it always drove me nuts because I would get reviews that said, well, these people who wrote this paper, they got security. How come you can't get as good a security as them? Because they don't have security. It drove me nuts. It was absolutely mind-boggling that stuff was accepted. But it's surprisingly, that's what I mean when I say surprisingly common, like even at the peer-reviewed level, people writing papers on security are still making that misconception. It's very disheartening to me. Yes?
Is there ever a scenario where like you would do the hash and then also do something else to the hash, like something in-house just to make sure that it's different from, like to add a slight variation so that even if someone were to
Yes and no. I mean, not really. We typically don't. So the question is, would you do something more like hash a thing and then do something extra, add another step to it to obscure the hash a little bit more? We have a saying for that: obscurity is not security. So we're just obscuring the method that we use to hash. Like effectively, if you hash and then do something else, add something else to the end, the combination of those, the composition of those two functions is now your hash function. That's your hash function you use. So you didn't add any security if somebody knows that hash function that you use, if they know that extra little bit. So you're obscuring your hash function by doing that little bit extra. So you could kind of trick somebody, but you're not actually adding security in a cryptographic sense, in like a mathematically provable sense. So as soon as somebody finds out what the extra thing is you're doing, it no longer adds anything at all. So you're obscuring your methods a little bit, but you're not necessarily adding security. So it could prevent some attacks, but I mean, not really. Somebody can find that out. Like if somebody recovers the database and gets all those hashes, they're going to look at, this is what I would do. Not that I would be in this situation, but I would look at my own account where I know the original password and then start reverse engineering from there. Look at the hash and figure out the extra thing that you did. People always want to suggest, well, just hash it twice. That's the first thing I'm going to check. I'm going to hash it twice. You know, I'm just going to check things until I figure out. And if I have access to the database, I probably have access to your code too. I'm just going to look at your code and figure out what you're doing. So kind of would add security. It's generally accepted that we don't do that because it doesn't actually add security. We're basically going to start by brute forcing the algorithm itself and then start brute forcing passwords once we know your algorithm. And if we could do something extra that actually does add security, well, it's just going to be the next hash function. Somebody's going to publish that and be like, hey, let's all use this because it's way better. And then everybody's going to start using it. Like SHA-3 is out. SHA-3 has more properties over SHA-2, which is SHA-256 is based on SHA-2. I think everyone would start using that if it's actually something better. Unless, just like the other example, somebody wants to keep that to themselves and be kind of rude about it, I guess. So let's introduce this term entropy. Entropy, in essence, is the number of guesses that somebody would have to make, at least you've probably heard this term before, at least in the cryptographic communities. Entropy is a measure of the number of guesses that you would have to make in order to crack some cryptographic thing or some security thing. So if, for example, I have a password or some plain text, not necessarily password, but some plain text input that I'm storing a hash of, and it's one single lowercase character, and I advertise that. I have a hash. It contains the input was one single lowercase character. Well, in at most 26 guesses, somebody's going to crack that hash. In 26 hashes, it's not even going to be a millisecond or two for a processor to do that. And most of that time is going to be spinning up your app to begin with. It's going to take almost no time to crack that. I've seen people hashing single bits. Like there's only 2. Your entropy is 2 at that point. If you have 2 lowercase letters, this is going to increase exponentially, which is where we can finally get some security. It's going to increase exponentially. So 26 squared, if we have 2 lowercase letters and we're up to 76 guesses, increases really rapidly. If we throw in uppercase letters, increase what we call the alphabet size raised to the alphabet length, we're going to get 2704 guesses. It's going to increase very fast. We get the power of exponentiation on our side for this. Since these numbers start to get really big really quick, we tend to measure them in bits of entropy, which is the log base 2 of these values. So we're going to measure the bits of entropy, and once we say, just kind of as a general rule of thumb in security communities, if we have 80 bits or more of entropy, then we're going to label that as secure. We're going to put our stamp on it and be like, 80 bits, we're good. We're good at that point. 80 bits of security is typically our goal, just our rule of thumb goal. If we have that or more, we're feeling good. We're feeling good that somebody's not going to break that. I want to run some numbers. I'm going to keep it low tech today. We're just going to go to the calculator and run some numbers here. Do I even have a log base 2 on here? Maybe I'll go a little more high tech. So for our 26 squared example, log base 2 of that, we have 9.4 bits of entropy. Very, very far away from our 80. Let me zoom this in a bit. Very far away from our 80 that we need. But we can do a few things. We can increase the alphabet size and increase the length of the string. So our alphabet size, I like to use 90 as the alphabet size. You have uppercase letters, lowercase letters, the 10 digits, and then, what's the math? Like 15 special characters. So if we use our full alphabet, uppercase, lowercase, numerals, special characters, we'll call that 90, and we have a password of length 2. We're going to start getting a little more entropy, but most importantly, we have our full alphabet. If we go all the way up, well, it's going to spoil the answer right away. If we do our typical password criteria and have a completely random password using that entire alphabet, uppercase, lowercase, numbers, social characters, and we have a password of length 8, a strictly, purely random string from that alphabet, we're still a long shot from our 80 that we need. In fact, we can do a little bit of math here. Let's say somebody can guess. We'll give them 1 million guesses per second. If somebody can make 1 million guesses per second, which is very reasonable, especially if they're running this on a GPU, they can make a lot of guesses at a time, or they're running some specialized hardware. The cryptocurrency communities have really pushed how fast we can compute hashes for mining various Bitcoin and various other coins. Which a lot of them rely on SHA-256, which is still really common for passwords and everything. So they can use specialized hardware and GPUs and all this stuff to compute hashes extremely fast. A million is probably on the low end of what people are capable of who actually want to do this stuff. So this many seconds, this many hours, this many days. Oh, we're still pretty high. I guess we could give them more power. This many years. Still a century. Let's give them a little more power. Let's give them 1 billion guesses per second. I was a little light on the guesses. Usually I do it with 100 trillion per second. So I was expecting a lower number. Let's go back to days. A month and a half. So definitely not instantaneous. There's some good security here. But not impossible either. If somebody hacks your database, and then in a month or even a year or so, they crack your password and you're using the same password on every app, and they just compromise everything then. As soon as that algorithm goes ding and they spits out your password, you're done in 49 days. It's a while, but it's not ridiculous. And if they don't have superpowered GPUs and stuff, you're looking pretty good there. So let's go back to log base 2, and that's our 52 bits of entropy. Let's increase this just a little bit. Just go from 8 to 10. And our bits go all the way up to 65. Let's try to get one above 80. Ooh, one more. We'll have to go up to 13. Password of length 13, so not much longer than your minimum requirement, and you're all the way up to 84 bits of entropy. So let's take a look at what 84 bits of entropy looks like, and this is where I'm going to give them 100 trillion guesses per second. So this divided by 100, 1,000, million, billion, trillion. 100 trillion guesses per second. It's a lot, but it's not completely out of the realm of possibility. If they have a botnet with GPUs or a whole server room of servers spinning on this thing, not completely outrageous. Per second, per hour, per day, per year. And it's going to take them 8,060 years to break that, even at 100 trillion guesses per second. Nobody's breaking this password. Even just going from length 8 to length 13, nobody's breaking that password. If we want to go, maybe you want a length 20 password, you're really concerned about your security, that's a 10 to the 17 at the end there. We're getting into the order of magnitude where the sun is going to burn out before somebody cracks this hash. Even if they're using all of the available computing resources on the planet, they will not break this hash using a brute force attack, assuming that you have a completely random 20 characters out of that alphabet. So this is the power of exponentiation. The numbers grow extremely fast. And in the world of security, cryptography, hashing, and everything, we use that to our advantage all the time. We use the fact that exponentiation grows extremely fast to our advantage, whereas like asymptotic runtime analysis, the exponentiation really hurts us. Here we're using it to our advantage and saying, you want to break this, you better run your exponential algorithm, which just isn't going to finish. Like, you're not finishing this thing. If we go to 30, nobody's ever going to crack this thing. Barring something like, I'm blanking on the name, the light computers. What's the name? Quantum computers. Barring like quantum computers running Shor's algorithm, you're not breaking this stuff. Actually, Shor's algorithm doesn't even apply to hashing here. So that's our entropy. We want our entropy high. Over 80, we pretty much say we're secure. That's when it's several millennium, even with 100,000 guesses, 100 trillion guesses per second. We're feeling good at 80 bits, but if we go even higher, we're feeling even better. There's a problem with this is I had to qualify that every single time with assuming you have a completely random password, that you have strictly random, purely random bits, or purely random characters that you're drawing from that alphabet. This is never the case if a human is generating that password. We all have our ways to help us remember passwords, and if we have to remember a purely random string, it's freaking hard to do. So we tend to not do that unless you're using a password manager. If you're using a password manager, you get the sun will burn out before this is cracked type of security. If you're not using a password manager that generates those passwords for you, you're susceptible to a dictionary attack, which is where they take the lists and lists that the attackers have of common passwords, use common substitutions. We all like to replace our letters with those special characters and stuff to be able to remember these things better. Common patterns that people like to use for passwords. All the common stuff that people have, and guess those passwords first. So instead of just randomly guessing something like a brute force attack does, that just randomly says, let's take random arrangements of characters from this alphabet and guess literally every single one, Dictionary attack says, let's cut out the 99.99% of those that no human would ever use because they can't remember something that random. And we take advantage of the fact that humans like patterns and start guessing those patterns instead. These attacks are much more effective. Even if you're meeting the minimum criteria, you're not getting that 50, bits of entropy that we saw in the month and a half for a pretty powerful attacker to crack. You're not getting that security if it's something that's designed for you to remember. You're not getting that security, anything even close to that. And finally, there's rainbow tables. I won't go too in depth, but I have my TLDR of what rainbow tables are. So what we'd like to do is guess like every hash possible simultaneously. That's what a rainbow table is trying to do. So what a rainbow table does is pre-computes hashes. It'll take a value, take a guess, hash it, take that hash and convert it into another possible guess, usually by just truncating it. If you're trying to attack up to length 20, up to length like 12 or whatever strings, you're going to truncate it to that length, hash it again, truncate, hash it again, truncate. And when I say truncate, there can be an arbitrary function, whatever function they end up using, to take the hash into the next guess. And keep doing that millions, billions, trillions of times, however many times they want. And then get the first and last hash of that, what we call a chain, and store only the first and last hash of that chain. And then do it again and again and again and again. These things can run for years on really powerful machines to generate these rainbow tables, which is a table with just the first and last hash of potentially millions, billions, trillions of chains. And these things can get in gigabyte sizes, even just storing 2 hashes per chain, and each chain can be millions, billions, trillions long. So the hackers pre-compute all of these hashes, all of these chains, and then when they get so a lot of the computation is done before they even get the hash. So the time from getting a hash to cracking is important because that's time the user, and mind you, I'm speaking strictly from the attacker perspective. I don't do this stuff. I don't attack things like this, but I'm speaking from their perspective. The time from recovering that hash and getting the password is crucial because the user has time to change their password in that time. If you're taking a month and a half, like we saw in the entropy example, they're probably going to change their password at that time, especially if the organization detected the breach and notified everybody and said, change your passwords, and attackers on this. They're going to start cracking hashes soon. That time's important. A rainbow table takes all that time and pre-computes it. Now when you get a hash, you can crack that really fast. What you're going to do when you get a hash is go through the same thing. Truncate it, hash, truncate, hash, etc., until the hash matches one of the endpoints. One of the endpoints of one of those chains. That means you know what chain this is from. You go to the start of that chain, go through your same thing, hash, truncate, until you get the original hash. Then you back up one step, and that's the password. This is a rainbow table attack. Very scary, very effective attack because you do all this pre-computation. These things, I hear that they're available. I never went and sought one out. But you can go online and download these rainbow tables, gigabytes of rainbow table, and then launch this attack. Very effective, very scary. We don't like that. So what we do, and obviously I'm not speaking as the attacker anymore, what we like to do is salt our hashes. We said a little bit of salt. Those rainbow tables are completely useless. So what a salt is a random value that we append to the end of your password. Generate a random value, a very long random value, append it to the end of a password, then hash that total value, the password with the salt. Hash that, store it, and then also store the salt in plain text. The salt isn't adding any entropy. The user gets the salt for free. So it doesn't add any extra security, any extra entropy or anything in normal circumstances. But what it does is makes those rainbow tables useless because the vast majority, almost every single one of those hashes in those chains will not end with that exact salt. So all of that work that they pre-computed, useless. They have to just throw it in the garbage. Rainbow tables are pretty useless now. It's an outdated attack because in classes like this, we all tell you, salt your hashes. Salt your hashes. Make sure they can't use these rainbow tables. So rainbow tables attacks are very scary. Salt your hashes and completely render them useless. So they're not attacking you. So when you're a legitimate user, you submit your username and password, take that password, take the salt out of your database, append that salt to the end of the password, hash it, and check if the hashes match. So for authentication, the process is almost the same. You just append that salt, which is stored in plain text, and just verify that the hashes match. So that's all the same procedure there. But those rainbow tables just don't work anymore. And I'll revisit these last few slides next time. In practice, for your homework, you are allowed to use the bcrypt library, and it is strongly recommended. Bcrypt will generate salts, do the hashing, do the matching. It'll do all this stuff for you in just a couple of lines. And I don't want to guarantee anything, but I'll probably have demos of that at some point here. But look up the bcrypt library. It'll have all the methods that you need to be able to do all this. You can do it yourself. I don't recommend it. Defer to the library. But you have to add this library to your homework projects. And you're allowed to use it on your homework. You're allowed to use it on your projects without reports, et cetera. It's fully allowed, this library. And with that, I'll see everyone Friday.